students, in this video we are going to study recursively enumerable languages and Turing machine. On last two question papers, we can see questions from recursively enumerable languages, Turing machine and post correspondence problem. Turing machine. Turing machine is an automation whose temporary storage is a tape. This tape is divided into cells and each of which is capable of holding one symbol. With tape, there is a read-write head that can travel right or left on the tape, and it can read and write a single symbol. Mathematically, Turing machine can be represented by a finite non-empty set of states Q, a finite non-empty set of taped symbols tau, a special symbol named blank, which is an element of tape alphabet, a finite non-empty set of input symbols sigma, which is a subset of taped symbols, and a transition function with arguments q, x, where q is the current state and x is the current tape alphabet, with a mapping onto q dash yd, where q dash represents new state, y is the new tape symbol, and d is the direction of movement of read-write head, which can have values L or R. Q0 is the initial state and F is the set of final states. Turing machine as language acceptors. Turing machine can be viewed as acceptors of languages. A string W, which is an element of sigma star, is said to be accepted by Turing machine M if the string W is on the tape with a read-write head position on the leftmost symbol of W. Also, the machine started on Q0, the initial state. If after a sequence of moves, the Turing machine enters into a final state and halts, then the string W is considered to be accepted. If the Turing machine M does not accept W, then the machine M either halts in a non-accepting state or does not halt. Recursive language. A recursive language, which is a subset of recursively enumerable languages, can be decided by a Turing machine M. A language L, which is a subset of sigma star, is said to be recursive if a string W, which is an element of the language L, then there exists a Turing machine M which enter into an accepting state. Also, for a string W, which is not an element of the language L, then Turing machine will halt without reaching an accepting state. Hence, the recursive languages are also called Turing decidable languages. Recursively enumerable languages. A language L, which is a subset of sigma star, is said to be recursively enumerable if there exists a Turing machine M that satisfies one of these two conditions. Either the Turing machine accepts the string or it rejects the string. So if the string W, which is an element of L, is accepted by the Turing machine, then it reaches the accepting state and halts. If the Turing machine, which is not accepting that string, which may or may not halt without reaching the accepting state, then that string is not element in that language L. Recursive and recursively enumerable languages. If a language L and its complement are both recursively enumerable, then both languages are recursive. Also, the converse is also true. If L and its complement is recursive, then Consequently, both are recursively enumerable. Recursive and recursively enumerable languages. We could see one hierarchy of recursively enumerable languages. In inner circle, we can see the regular languages, which is a subset of deterministic context-free languages. And deterministic context-free languages is a subset of context-free languages, which can be non-deterministic too. And this context-free languages is a subset of context-sensitive languages. And this context-sensitive languages is a subset of recursive languages. And this recursive languages is a subset of recursively enumerable languages. Post correspondence problem. Let A W1, W2, W3, etc. Wn and B V1, V2, V3, etc. Vn are two sequences of n strings on alphabet sigma. Then it has a solution if there exists integers I, j, k such that wi, wj, etc. wk equal to vi, vj, etc. vk. For example, sigma equal to set 0, 1. A be a sequence of string w1, w2, w3 and B be another sequence of strings v1, v2, v3. Here we could see one sequence of integers 2, 3, 1 such that w2, w3, w1 equal to v2, v3, v1. Undecidable properties of recursively enumerable languages. There exists no algorithm for deciding the following properties of recursively enumerable languages. Membership problem. For a given string W and a language L, we want to check W is an element of L. That is called membership problem. Next one is finite or not and empty or not. If L1 is equal to L2 or L1 is a subset of L2 and L1 intersection L2 equal to 5, there exists no algorithm for deciding these properties of recursively enumerable languages.